Welcome to AI Paper Podcasts. Today's paper is The Appeal and Reality of Recycling LoRAs with Adaptive Merging by Haokung Liu and team. Here's the premise. ML engineers are constantly uploading specialized LoRAs, or low-rank adaptations, to Hugging Face. Can we recycle this massive free pool of knowledge by merging them to solve new, unseen tasks?
The reality check is no. While merging public LoRAs beats a base model, it almost always loses to a simple LoRA trained on just 100 target task examples.
And here's the twist. If you include your target task LoRA in the merging pool, adaptive merging works. But you don't even need real recycled LoRAs to do it. You can merge your target task LoRAs with completely random initialized weights and get the exact same performance boost.
Meaning the recycled knowledge is mostly just acting as a mathematical regularization effect. It is not actual positive transfer.
Okay, that is the 60-second summary for the short edit. Now, if you are an AI researcher or ML engineer trying to figure out why your merged models aren't generalizing, stick around for this deep dive.
Because if you're tired of playing Hugging Face roulette, this is exactly what you need to hear.
Yeah, so let's set the context. We are looking at the explosion of parameter-efficient fine-tuning, or PEFT, because updating a massive base model is incredibly expensive.
Right, it takes a fortune in GPU compute.
Exactly. So instead, you freeze the base model and just attach these tiny condensed matrices. Since LoRA updates are represented as low-rank products, they're super cheap to train and share.
Which is why hubs like Hugging Face are just flooded with them right now. I mean, the authors of this paper specifically looked at over 1,000 fine-tuned variants of just the Llama 3.1 8B instruct model.
As one model.
Yep.
And that naturally leads to this dream of model merging. Like, if we have all these specialized experts sitting on the hub, can we combine them?
That's the hypothesis. Yeah, you have static methods like simple averaging or ties.
Yeah.
But the holy grail here is adaptive merging.
Right, methods like LoRa Hub or adder merging. The goal there is to tune per model coefficients using a tiny data set. So you feed it a few examples of your new task, and it creates a supermodel that transfers knowledge from those constituent LoRAs.
But this paper does something really different. Past research mostly used bespoke, in-house LoRAs to prove their merging worked. Clean environment.
Sterile, yeah.
Exactly. This paper downloaded 958 real messy, user-contributed LoRAs straight from Hugging Face.
And if you're an ML engineer, you know how wild that pool is. The diversity is insane. Different ranks, like 8, 64, 256.
Different targeted transformer blocks.
Right, attention versus feed-forward layers. And completely undocumented data sources.
Which makes this a truly realistic testbed. They tested these 958 LoRAs across 62 highly diverse downstream tasks.
Like math sets, AquaRA, GSM-8K, document understanding.
Even multilingual inference like XNLI. And crucially, they assumed access to just 100 target task samples.
Which is very realistic. 80 for training the coefficients, 20 for validation. That is what most startups are actually working with.
Yeah, you rarely have massive labeled datasets for a highly specific new task.
So to tackle this, the authors built a unified framework to test merging configurations. I love this part because they mapped out the entire design space into 4 core pillars.
The 4 pillars of adaptive merging. First up is selection. How do you pick 30 LoRAs out of 958?
Right, because you can't merge all of them.
Exactly, the compute would be absurd. So you could pick them at random. Or use evaluation-based selection, testing them on your 80 samples. Or cosine similarity. Or even a quasi-Fisher information matrix.
Quasi-Fisher information matrix. That sounds intense, but it basically gauges how sensitive the model is to parameter changes.
It finds the structurally critical weights.
Yeah.
But moving to pillar 2, granularity. Where do you actually apply these coefficients?
Because you could just apply one multiplier for the whole model.
The model level.
Yeah, right.
But you lose all the nuance. Then there's the layer level, the sublayer level.
Separating attention and feed forward.
And finally, the module level, assigning separate coefficients for the query, key, and value matrices.
Which is critical because one LoRA might be great at French syntax, but terrible at math reasoning. You need module-level granularity to isolate those specific skills.
Spot on. Which brings us to pillar 3, activation. How do you transform the raw coefficients?
The options being softmax, linear, or leaky ReLU. And this is fascinating because softmax forces everything to sum to 1, right? Pure interpolation.
It's very safe, but highly limiting. It's like mixing blue and yellow paint to get green. You stay within the bounds of your existing weights.
But a purely linear activation gives the optimizer too much freedom.
Right, that's extrapolation. Trying to get neon pink from blue and yellow paint, it shatters the model's structural representations.
Which is why leaky ReLU is the sweet spot. It allows mostly positive coefficients for constructive merging, but permits very small negative values.
It lets the optimizer slightly extrapolate away from a conflicting parameter without completely breaking the model.
And the final pillar is tuning.
Right. Gradient-based tuning using standard backpropagation versus gradient-free methods like LoRa Hub.
So the authors ran this massive ablation study across all these choices, and the winning formula, their custom method, used module-level granularity, evaluation-based selection, gradient-based tuning, and leaky ReLU.
The optimized pipeline.
The absolute best-case scenario for merging. So let's look at the reality check. Round 1, merging versus prompting.
The good news is, merging 30 recycled LoRAs with this adaptive method substantially beats zero-shot prompting of the base Llama model.
Huge win, although Tai's merging struggled here.
Yeah, Tai showed almost no improvement. It's really sensitive to hypoparameters and was designed for full fine-tuning.
Not heterogeneous LoRAs. It can't resolve the sign disagreements across all those different ranks and modules.
Exactly. But let's move to round 2. This is the 100-sample elephant in the room.
Yes. Because if you have 100 samples to tune your merging coefficients, you also have 100 samples to just train a brand new LoRA on your target task.
The target task baseline.
Yeah.
It's so simple, but prior papers ignored it.
And the crushing result is that when compared to that simple target task LoRA trained on the 100 examples, the complex adaptive merging methods essentially fail.
They don't produce meaningful improvements. And if you don't include that target task LoRA in your merging pool, you perform worse.
Methods like LoRa Hub show almost zero positive transfer without it. You absolutely must include the target task LoRA in the pool.
Which leads to the most mind-blowing part of the paper.
The selection strategy breakdown. Because once you put your target task LoRA in the pool, does it matter which 30 Hugging Face LoRAs you select?
You'd think so, right? But the researchers found that the performance gap between carefully selecting the best LoRAs and just picking 30 at random completely disappears.
Disappears entirely. You can evaluate all 958 models, spend all that compute, and it yields the exact same accuracy as grabbing 30 random files.
Which prompted the random initialization bombshell. They decided to throw out the Hugging Face LoRAs completely.
They just generated fake LoRAs.
Completely random parameters sampled from a normal distribution. Literally just noise. And they merged those with the target task LoRA.
And the result? The randomly initialized LoRAs performed comparably to the actual recycled LoRAs.
It's incredible.
But how? How does adding random mathematical noise increase accuracy on complex tasks?
You have to look at the coefficient distribution. When the optimizer is tuning the weights, it spots the target task LoRA immediately.
Because it's the only one that actually knows the specific task.
Right. So it assigns a massive weight to the target task LoRA, and it flattens the other 29 LoRAs to tiny, almost uniform coefficients.
So those 29 random noise LoRAs are just being mathematically squashed.
Exactly. They aren't transferring knowledge about math or coding. They are acting as a mathematical regularizer.
Because training LoRA on just 100 examples makes it incredibly prone to overfitting. It just memorizes the data.
Yes. But by forcing the optimizer to balance 29 other random matrices, you apply a structural friction. It prevents the target task LoRA from updating too aggressively and overfitting.
So the boost we thought was recycled knowledge from Hugging Face is just a convoluted regularization effect.
That's the reality of it.
Which is a huge reality check for any ML engineer listening.
Yeah.
You might be burning compute searching the hub for a regularization effect you could get with static noise. But why did past papers claim such massive success?
Because of the controlled versus real-world discrepancy. Past papers used in-house LoRAs.
Curated, consistent models.
Exactly. The researchers proved this by creating an in-house pool from their 62 tasks. And when they merged highly relevant in-house LoRAs, they did see real positive transfer.
It beat the target task LoRA baseline without the random noise effect taking over.
But then they did the sliding window of decay experiment.
Right. They took that successful in-house pool and systematically removed the top 5 most relevant LoRAs.
Then the top 10, then 15, then 20.
And as soon as those highly relevant tasks were removed, performance plummeted right back down to the level of random noise.
The core takeaway is that real-world transfer relies heavily on highly relevant source LoRAs.
And despite having nearly 1,000 LoRAs, The Hugging Face pool is simply too sparse and noisy to reliably provide that perfect match for random downstream tasks.
So synthesizing all this for you, the practitioner. Before you build a complex adaptive merging pipeline, always verify your method against a simple LoRA trained on your exact target data.
Do not trust benchmarks that don't use real in-the-wild pools or that skip the 100 sample baseline.
We really need better metadata, licensing, and standardized training providences on hubs before recycling becomes a reliable utility.
It changes everything about how we view these open source repositories. But I want to leave you with a final provocative thought.
Go for it.
If merging 30 completely random LoRados with your target LoRa acts as such a powerful regularization tool, mimicking knowledge transfer, could we intentionally design structured noise adapters during few-shot fine-tuning?
Oh, that's interesting.
Right. Instead of hunting for the perfect Hugging Face model, perhaps the future of preventing overfitting in low-data regimes lies in systematically merging your model with specifically calibrated mathematical noise. You could instantly generate a localized pool of random adapters on your own hardware and achieve robust generalization with zero reliance on external hubs. Something to think about for your next pipeline.